In the previous videos, we have discussed the position of the Sun with respect to a PV module lying horizontally on the ground. However, if you want to increase the irradiance on the surface of the module, then the module should be tilted. In this video, we will give you the tools to calculate the irradiance as a function of the tilt angle and the azimuth angle of the PV module. To that end, we will first divide the incoming irradiance in direct, diffuse, and albedo components. In order to calculate these components, we first have to introduce a very important parameter, which is the angle of incidence. As mentioned, you could simply place a PV module flat on the ground. In that case, only one component of the global irradiance is enhanced. For a horizontally inclined module, the diffuse component is increased because the module can receive light from the entire hemisphere. Let's have a look at the system that we would like to optimize. Here we have the solar module mounted on a plane, tilted at a certain angle θm. The irradiance that is incident on the module can be divided into three components. The direct irradiance is directly incident on the module. The diffuse irradiance is the solar radiation that reaches the module surface after being scattered by molecules in the atmosphere. Finally, the albedo is the part of irradiance that reaches the module after reflection by the ground or objects in the neighborhood. At the end of this video, you will be able to calculate with reasonable accuracy the three components on a cloudless sky. However, before showing you how to calculate each component, I will introduce some important terminology. In this picture, our PV module is tilted with respect to the ground at an angle θm. Here we can describe the position of the module according to its normal vector, which is the one highlighted in red, that identifies a point in the celestial sphere. This point can be located in the horizontal coordinate system by means of two coordinates. First, we need the azimuth of the module, which is the angle between true north and the normal of the module projected on the horizontal plane. Be careful to not confuse the azimuth of the module with the azimuth of the Sun. The second coordinate we need is the altitude of the module, which is complementary angle of the module's tilt as written in the equation. Now, let's have a look at the angle of incidence. The angle of incidence is the angle between the module normal, depicted by the dashed green line, and the incident direction of the sunlight, represented by the red beam. So, we indicate the angle of incidence in this figure in red. In the top of the slide, you can find the trigonometrical equation used to derive the angle of incidence. You can see that it is only a function of the azimuth and altitude of the module normal and the Sun position. The derivation of this equation can be found in the solar energy book. It is important to realize that this is drawing in a two-dimension. This means that the angle of incidence highlighted in red is true only in case the azimuth of the module corresponds to the azimuth of the Sun. Now we have all the tools to divide the incident irradiance into the three components we introduced earlier. The direct component can be calculated using the following equation. We can notice that the direct irradiance component is proportional to the direct normal irradiance, or DNI, times the cosine of the angle of incidence, which we have just derived. The other component that contributes to the incident global irradiance is the diffuse component. There is not a single unique equation to obtain the diffuse irradiance. The calculation of this irradiance depends on the sky model that you want to use. Sky models differ in complexity, but in general they are a function of the diffuse horizontal irradiance, the angle of incidence, and most important, the so-called sky view factor, or SVF. This parameter only depends on the tilting of the module, and it represents the portion of the sky seen by the module. As the tilt angle increases, the portion of the sky that the module faces decreases. For example, when the tilt is 90 degrees, then only half of the sky irradiance can be received by the module, and indeed, the cosine of 90 degrees is 0, and the equation gives 0.5. Therefore, when the module is flat on the ground, light is incident on the module from the entire hemisphere. On the other hand, when the module is tilted, in order to optimize the direct irradiance, the angle from which light can reach the module is limited, and therefore the sky view factor has to be calculated. Here we show a couple of sky models with varying levels of accuracy. First of all, it is important to understand that the diffuse radiation from the sky is typically subdivided into three components. The isotropic component represents the uniform irradiance from the sky. The circumsolar diffuse component, which represents the forward scattering of radiation concentrated in the area immediately surrounding the Sun, is the second. And finally, the horizon brightening component. Sky models use different semi-empirical approaches for estimating the combination of these components. The simplest one is the isotropic sky model. The isotropic sky model assumes that the diffuse radiation is uniform across the sky and is only a function of the sky view factor and the direct horizontal irradiance. Then we have the Sendia model. The Sendia model also takes the circumsolar and horizon brightening into consideration by means of an empirical formula that is a function of the sky view factor, diffuse horizontal irradiance, and global horizontal irradiance. The Hay and Davis model is a bit more complex. It requires measurements of the DHI and then corrects for not only the sky view factor but also for the angle of incidence. It takes into account isotropic and circumsolar components. Finally, the Randall sky diffuse irradiance model uses all the three components of diffuse radiation, including isotropic, circumsolar brightening, and horizon brightening. It does not rely on DHI measurements, and this allows for direct use of the GHI. The Randall sky diffuse irradiance model is quite powerful and very accurate for a country like the Netherlands, since it was developed for locations with the high latitudes like Northern Europe. As you might notice, the complexity of the models increases until we include all three components of diffuse radiation. And now we see the last component of the irradiance, the albedo. The module receives radiation that is reflected from the ground and the surrounding environment, which can be approximated by this equation. GHI, as we have already seen, is the global horizontal irradiance, and alpha is the albedo coefficient, which expresses the reflection from the ground and the environment. The lower the albedo, the more light is absorbed by the ground and the environment. For example, the albedo of forests is around 0.1, that of snow is 0.6, the albedo of urban areas is between 0.05 and 0.2, the albedo of water is merely 0.1. The albedo can be measured with an albedometer. This consists of a pair of pyranometers mounted parallel to the ground. One pyranometer is pointing downwards to measure the intensity of reflected light from the ground. The other pyranometer is pointing upwards to measure the GHI. The ratio between these two quantities is the coefficient alpha. To recap, let's go back to this sketch. We divided the irradiance incident on the surface of a module into three components. The direct irradiance can be calculated by multiplying the direct normal irradiance by the cosine of the angle of incidence. The latter was derived using trigonometry. The second component is the diffuse irradiance, which depends on your choice of sky model and the available measurements. Generally, the diffuse irradiance is a function of the sky view factor, the DHI, and again, the angle of incidence. The third component is the albedo, and it depends on the global horizontal irradiance, the albedo value of the surrounding ground, and again, the sky view factor. The formula to compute this factor depends only on the tilt angle of the module, and it is necessary to obtain the diffuse and albedo components. In the next video, we will discuss how to find the optimal tilt angle.